Section 6.3 is about simplifying radical expressions. And really what this all kind of runs on is one of the specific laws of exponents. Specifically, it's the one about where usually if you're using it as a law of exponents, it's where you have a product raised to a power and then you distribute the power to the individual factors of the product. That's basically what this is right here, just written in the reverse order, where then you have the individual factors raised to a power and then you can combine it together as a product raised to a power. And then it's just a little more specific in what kind of power you have, in the sense that you have a root. So that's essentially how this is going to work. Most of what we're going to do is actually going to be going right to left in the thing that's circled in blue right now rather than left to right, but the first page has some left to right. So I guess to say it all in words, the product of the roots will be equal to the root of the product. And really this is just one of those laws of exponents. And that justification's right there, where if you switch the notation from writing with the root notation into writing with exponents, where you would use the rational exponent 1 over n for the nth root, then you can see it, where then you have a to the 1 over n times b to the 1 over n. And then you can combine that together as a times b raised to the power of 1 over n. So to do something a little bit more concrete, we have the square root of 7 times the square root of 2. Then we can say, well, then that'll be the square root of 7 times 2, which would be the square root of 14. And this will work as long as we have the same root. We can do this sort of thing. So we have 2 square roots in number 1. We got 2 cube roots in number 2. So it'll still work here. And we can write this as the cube root of 3 times 11. But 3 times 11 is 33. So that's the cube root of 33. 3. Okay, we've got variables showing up now, and that's okay. We've still got 2 square roots multiplied together, so we can rewrite that as the square root of n plus 4 times n minus 4, but those are conjugates, so this will be the square root of n squared minus 16. Actually, this is a thing, I want to make sure I mention this. We won't need it in this section, but we might need it in the very near future. If you're going the other direction, watch out. So if you have something like this, and you have to simplify it, this is not going to be the same as the square root of n squared minus the square root of 16. Right? Clearly it's something else if you look at what the original problem was in number 3. That thing that I just wrote in maroon, that's sort of it's a common mistake that I think everybody kind of makes at some point. So I guess it's sort of like a trap to avoid. That might be a good way to put it. But I did want to mention that because I think that might be a thing that shows up. Like I said, it won't be in this section, but maybe within the next couple. All right, then number 4, 2 fifth roots. Well, it's an unusual root, but it's 2 of the same kind of root. So we can still do what we've been doing and say that'll be the 5th root of 7a to the 3rd times 3a. And then we can multiply underneath that radical and say that's going to be the 5th root of 21a to the 4th. Okay. So most of what we're going to do is actually going the other way, where we start off with just a single root and then try to simplify it from there. So simplifying a radical expression, basically what you do, the thing that would simplify it is if you can make what's under the radical a simpler expression. And the way that you can do that is that if you have a perfect nth power that's a factor of what's under the radical, that's where you can break the radical up into a product of radicals. And then when you have the nth root of an nth power, you can simplify that to where that's not expressed with a radical anymore. So the first thing is to see if you have any perfect nth powers. So in step 1 where I have that indented bullet point, so for example, where there's the square root of 12x cubed, and then that's broken up underneath the radical, and there are parts that are in blue. Those blue parts are the perfect squares, because that's a square root. So here the perfect nth power would be the second power, so it would be squaring. So with the 12, what you'd be looking for is, are there any factors of 12 that are a perfect square? Other than 1, because 1 doesn't really help us at all. But you go, well, yeah, 4, right? 4 divides 12, and 4 is a perfect square because it's 2 squared. So we can write 12 as 4 times 3. And then for the x cubed, there is actually going to be a perfect square that's a factor of x cubed, which is x squared, right? You could write x cubed as x squared times x, but x squared is a square, right? I mean, I guess sort of by definition it's a square, but certainly that's going to be the case. All right, then what you can do is you can rewrite that expression as the product of 2 radicals. So now we're into the second step, one of which would be that nth root of the nth power. So what I did was I said, all right, we've got the 4 times 3 times x squared times x. I'm going to rewrite that so that the perfect squares are next to each other. So 4 times x squared times 3x. So basically what I have is, so that thing that I just made an arrow pointing at it, there's something that's a perfect square, right? And then there's the 3x next to it, and the 3x, we can't really do anything with that. But we can separate this out and say, all right, we've got the square root of the perfect square times the square root of 3x, and that square root of 3x is just going to stay there, right? We can't break that down any further. Then when you simplify the nth root of the perfect nth power, the square root of 4x squared, you could then rewrite as the square root of 4 times the square root of x squared. And then you say, well, the square root of 4, that's 2. Then the square root of x squared would be the absolute value of x, right? Assuming that x can take any real value, including negatives, then it would be the absolute value. So you'd have 2 times the absolute value of x, and then that square root of 3x is still in there. And then I just wrote it without the dots for multiplication. All right, so other things that are going to help with this in general. If n is even, then the nth root of a to the nth power is the absolute value of a, if a is allowed to be any real number. And then if n is odd, then the nth root of a to the n is just a. The other thing that shows up almost immediately is this, but this doesn't always get used in this section. Usually this is the case. So there's a point where, like, if you don't have that assumption, then you need the absolute value. Like for an even root, like where there's the nth root of a to the nth power equals the absolute value of a if n is even, then you need the absolute value. If you assume that the variable is non-negative, you don't need it, because then it wouldn't take negative values anyway. So then the absolute value of a non-negative number is just that number, and then you don't need the absolute value symbols anymore. But this isn't always used in this section. At the very beginning of the section, our book sticks with the absolute value, and then there's a point where it switches, which is where the expressions under the radical start to get complex. So usually this is the case. So I guess I'll just say some problems toward the beginning of the section do not use this assumption. All right, so I think it would depend on what the problem said. If the problem said, like in the homework, if it said that the variable is allowed to be any real number, that's where you need the absolute value. Otherwise, if that assumption is going to take hold, then you wouldn't need it if there's the assumption that the variable can only take non-negative values. So I would say, unless stated otherwise, that assumption is probably going to be there. Um, just based on the way that it's worded in the book and when I ran the preview of the homework assignment. That's what I would anticipate. All right, so moving forward to actually simplifying some stuff. So square root of 24. Okay, just a number underneath the radical, and then we just have to see, are there any perfect squares that are going to divide that? Yes, 4. So we can rewrite 24 as 4 times 6. And then I'm going to break this up into two radicals where I have the square root of 4 times the square root of 6, but then the square root of 4 is 2. So this is 2 radical 6. And we can do a similar thing with number 6, even though it's a cube root. And if you don't see this right away, it might be helpful to kind of cycle through the cube roots, or the perfect cubes, rather, mentally. And I'm going to write some of them up toward the top of the page, just in a different color. So let's see, what might help us? 2 cubed, well, that's 8, which does divide 128. 3 cubed is 27, that's not going to help. 4 cubed is 64, that divides 128, and it's bigger than 8. So you could use either of those, but if you use the bigger one, you'll get there faster. You'll get to the fully simplified version faster. So I want to use that 64 rather than the 8 to break up that 128. So another thing with, if you have to cycle through the powers, which you probably don't need to do for the squares necessarily, but maybe for the cubes or for the powers of 4, like they're harder to remember. You don't use them as much, right? I mean, they're harder to remember for me too. Like I cycle through them a lot. Once you get up to about half of whatever that number is, there's no need to keep going. Right? Because anything beyond that's going to be too big. There's no way that, beyond 4 cubed, the next one is 5 cubed, which is 125. That's way too big, right? There's no way that could divide 128 evenly. So I guess mentally when I do it, I just go up to around half of whatever that number is. And if I don't find anything by then, I just kind of go, all right, then that's that. Then I guess we can't really do anything. But here we actually have 2 of them that'll work, and the 64 I think is it's the better choice in the sense that you'll get done faster. And oops, I meant to make that 2 as a coefficient. So that's 2, and then the cube root of 64 times 2. And so then we can break that up and say that then that'll be 2 times the cube root of 64 times the cube root of 2. But the cube root of 64 is 4. So that's 2 times 4 times the cube root of 2, or 8 times the cube root of 2. With the homework, they aren't going to want that multiplication dot in there. But for me writing it out by hand, when it's any other root besides a square root, I like to put it in there just so that way that the number that's there for the root isn't on top of the coefficient. So then it's clear that that's a root and it's not like 8 being raised to the 3rd power times radical 2. So I always write it kind of reflexively, that multiplication dot, but you probably don't want to include that with the homework. Number 7. Let's see. So this time we have a coefficient of 75, and then we have a variable. We've got an x squared. Okay. Well, the x squared, that's already a perfect square, but then the 75, let's see. 4 doesn't help us. 9 doesn't help us. 16 doesn't help us. 25 does. So we're going to rewrite 75 as 25 times 3. And then we're still going to have that x squared in there. So then what I'm going to do is I'm going to rewrite the order here so I have the perfect squares next to each other. So 25x squared times 3. And it might be easier just to go ahead and break this up into 3 square roots. So the square root of 25 times the square root of x squared times the square root of 3, because we'll be able to simplify those first two. Right, the square root of 25, that's 5. The square root of x squared, if you're working under the idea that x can be any real number, including negatives, then you would need to write the square root of x squared as the absolute value of x. And then if you're working under the assumption that x is non-negative, then you wouldn't need the absolute value. And then that radical 3 we can't really do anything with, so it's just going to be there at the end. So just to write this without the multiplication dots, 5 absolute value of x, radical 3, like that. And then if x is non-negative, then it would just be 5x times radical 3. But this one, it came out of the extra bank that goes with the early part of the section, so I figured that's one where adding in the absolute value is probably going to be the right idea. Let's see, number 8, 4th root of 50. Okay. Let's see what the perfect powers of 4 are. So let's see what we've got here. 2 to the 4th, well, that's 16. That doesn't divide 50. 3 to the 4th is too big. It's 81. So what does that mean? So this is not a factor. And clearly the 81 can't be, right? It's bigger than 50. So, all right, well then that means that the 4th root of 50, this cannot be simplified. And I think this will occur in the homework for this section. Once, maybe twice, but I think it's just once where you get one that doesn't simplify, right? We can't do anything with this. If it was the square root of 50, sure, right? Then you go, well, then 25 is a perfect square, right? We can do something with that. But the 4th root, there's just nothing we can do with it. All right, then number 9, square root of 18y to the 8th. So the y to the 8th is a perfect square because the exponent's a multiple of 2. So then we just have to see what we can do with the 18. And you think, all right, well, 4 doesn't do anything, but 9 does, right? We can have 9 divide 18, since 18 is 9 times 2. So we can say, well, then this will be the square root of 9 times 2 times y to the 8th. Then, let's see, if I rewrite this, then we can say, well, this will be the square root of 9 times the square root of, I'm going to move the y to the 8th forward, right? It's multiplication. You can switch the order if you want to. And that way we've got the perfect squares next to each other. And then times the square root of 2. So we know what the square root of 9 is. That's 3. The square root of y to the 8th is going to be y to the 4th. And if you don't see it, you could rewrite it this way, as y to the 8th to the 1 half, right? If you rewrite the radical notation as exponential notation, and then we've got the radical 2. And then for that part that's in the middle, the y to the 8th then to the 1 half, if you multiply the powers together, that's going to be y to the 4th, right? So this will end up being 3y to the 4th. And that 4, as usual, did not turn out that well. So 3y to the 4th times radical 2. Okay. And let's see what we can do with number 10, because it looks pretty similar. With number 10, we'd need a perfect square, the biggest one that divides 48, because 4 would work, but 16 would work better. So this will be the square root of, and we can write the 48 as 16 times 3. And then we can also write the x cubed as a product where one of the factors is itself a square. We can write that as x squared times x. So basically what you want to do if you have to rewrite a variable raised to the power, you want one part of that product, so one of those factors, to be the largest power that's a multiple of, in this case, 2, because it's a square root. If it was like a fifth root, then you'd want the largest multiple of 5. Right? But here, square root, and I guess the largest multiple of 2 that's less than 3 is 2 itself. So that's really about all we can do there. And then we can rewrite this. Let's see. I guess break it up as a product of roots, and we'll put the square roots of perfect squares in the front. So square root of 16, square root of x squared, and then what's left? We got a 3 and an x. All right, that's the square root of 3x. And that we won't really be able to do anything with. But the square root of 16, that's 4. Then if we're assuming that x can only take non-negative values, then square root of x squared would be just x, and then times the square root of 3x, like that. Oh, and the thing about the absolute value, so here, yeah, if x could be any real number, you would need it, but if you work under the assumption that it's only going to take non-negative values, then you don't. In number 9, it actually wouldn't matter because it's a y to the 4th that you end up with, and that's non-negative anyway, right? Anytime you got the variable raised to an even power, you're not going to get a negative out of that, right? So there it actually wouldn't have made a difference. I guess that's the sort of thing where if you put in an absolute value symbol, then that would be redundant. All right, so let's see then. 11, that's a cube root. So let's see what we can do here. This might be easier just to break this up into 3 pieces. So like the coefficient part, the a part, and the b part. So I'm going to write it that way. Is the cube root of 8 times the cube root of a to the 5th, and then times the cube root of b to the 10th. Well, the cube root of 8 is just 2. All right, but then we can rewrite the cube root of a to the 5th. So I want to write that a to the 5th involving the largest power of 3 that's less than 5, which is just 3. So I'm going to write it as a cubed times a squared, and then times the cube root of, let's see, I need the largest power of b that's a multiple of 3 that's less than 10, which is 9. So I can write this as b to the 9th times b. All right, so then let's see what we can do. We've got the 2, then the cube root of a cubed, then cube root of a squared, then a cube root of b to the 9th, and then a cube root of b. Okay, so we'll have a 2. The cube root of a cubed is a. Then the cube root of b to the 9th is going to be b cubed. And then what we have left over is the a squared and the b. We can't really do anything with those. So we'd have the cube root of a squared b. So I had to rearrange the order a little bit, move up that b cubed, since that's one that we can actually simplify. But that's what we're going to end up with there. All right. Let's see, 12, 13, 14. With those, we've got to do some multiplication first before we simplify. So if you look at 12, you can't simplify radical 2 any further, and you can't simplify radical 14 any further. But when you multiply them together, there might be something we can do. So it's the same kind of root, right? They're both square roots. So we can say, well, this will be the square root of 2 times 14, but 2 times 14 is 28. But there is a perfect square that divides 28, which is 4. So then we can write this as the square root of 4 times 7, and then break that up as the square root of 4 times the square root of 7, but the square root of 4 is 2, so this is 2 radical 7. And that kind of thing is also going to be what happens with 13 and 14. There's just more going on with those because they've got variables in them. So with 13, we can say, well, this will be 2 times the cube root of 9x squared times 3x squared. But then we can write that, so the thing that's underneath the radical, we can simplify that as 27x to the fourth. All right, so then let's see. 27 is a perfect cube. So we can say, well, this will be 2 times the cube root of 27 times the cube root of x to the fourth. So we know the cube root of 27 is going to be 3. So 2 times 3, and then underneath the radical, I'm going to rewrite that x to the fourth as x to the third times x. So I'm going to use the largest exponent that's less than 4 that is a multiple of 3, because then we can break this up into 2 radicals. So I guess the 2 times 3 we can write as 6. And then that'll be times the cube root of x cubed times the cube root of x. But the cube root of x cubed is just x. So this is 6x times the cube root of x. And that's as far as we can simplify that one down. All right, let's see with 14, what can we do there? All right, so it'll be the fourth root of, if we multiply things together, 8 times 12 is 96. Then we're going to have m to the power of 3 plus 2, which is 5. And then n to the power of 6 plus 9, which is 15. Okay. Then let's see. With the 96, and this is actually a good point to bring this up. When you're simplifying expressions like this, a lot of times the coefficient is harder to deal with than the variables, because the coefficient might be a number where it's hard to see what perfect power you need to use as a factor. And usually with the variables you can see it, because even here, like 15 is a pretty big exponent, but that's not really that big of a number, right? So like if you're looking at that and thinking, all right, I need the largest multiple of 4 that's less than 15. Oh, it's 12, right? It doesn't take that long to figure that one out. But with the 96, even though that's one where you think, all right, if I need the biggest perfect fourth, all right, well, let's see, what are they to begin with, right? So 16, that's 2 to the fourth. And then 81, that's too big to really help us. But 16 works, right? Because 16 times 6 is 96. So 16 actually does work. Let's see what we can break up here. So we can rewrite that 96 as 16 times 6. Then we need the largest multiple of 4 that's less than 5, which is 4. So we can write m to the fifth as m to the fourth times m. And then n to the 15th we can write as n to the 12th times n to the third, right? Largest multiple of 4 that's less than 15 is going to be 12. All right, well then we can kind of rewrite this. So I'll put all the perfect fourths in the front. So fourth root is 16 times the fourth root of m to the fourth times the fourth root of n to the 12th times the fourth root of what's left over, which looks like it would be 6m n cubed. Those are the parts that we didn't use. So let's see, fourth root of 16, that's 2. Fourth root of m to the fourth is m, if we're assuming that m can only take non-negative values. Then fourth root of n to the 12th is going to be n cubed, and then times the fourth root of 6m n cubed. All right. The next thing, which is the next couple of examples, it's a similar idea, but it looks a little bit different. There's part of the simplification where you have to be pretty careful, though. So we're still going to try to simplify the radical. So with 15, we've got the square root of 63. The biggest perfect square that's going to divide 63 is 9. So we can write this as 6 minus the square root of 9 times the square root of 7 over 3. But the square root of 9 is 3. So this is 6 minus 3 radical 7 over 3. And this can actually simplify a little bit farther because the numerator has a common factor of 3. Right? 3 divides 6 and 3 divides 3, the coefficient of 3 radical 7. So what we can do is we can factor out a 3 on top, and we'd be left with 2 minus radical 7 over 3. And so then those 3's could cancel out, and then the answer is really 2 minus radical 7. The thing that's the common mistake here that I think you have to be really careful of, because this is a really easy mistake to make, is right off the bat to cancel the 3 with the 6. Then that's a bad idea. And the reason that you can't do it is because the numerator's got 2 terms in it. It's got the 6 and it's got the radical 63. So if you can cancel, you've got to do it when you've got a multiple of 3 factored out, which we were able to get, right? Since we were able to rewrite the square root of 63 as 3 radical 7, then you can factor the 3 out of the numerator and then cancel it. So by the same token, with number 16, the thing that you don't want to do right off the bat is to cancel the 2 with the 10, because then you also have to be able to cancel the 2 with the other term, that square root of 72x squared. So you got to make sure you get both terms in the numerator when you're canceling. And the easiest way to do that is just simplify that radical first and then see if you can factor anything out. Just factor anything out of the numerator. And then see if you can cancel the 2 with whatever you can factor out. So let's see. Then we've got 72x squared under the radical. Biggest perfect square that's a factor of 72 is going to be 36. So we're going to have 10 plus the square root of 36 times 2 times x squared all over 2. All right, so I'm going to rewrite that root as the square root of 36 times the square root of x squared. And since we can simplify that, and then times the square root of 2. So I'll just put again, the part that we can't simplify, I'm just going to put at the end. And then divide by 2. All right, so we've got 10 plus 6x radical 2 over 2, right? Since the square root of 36 is 6, square root of x squared is x. And then in the numerator, we've got a common factor of 2 since both coefficients are even. So we can factor out a 2. And we'll be left with 5 plus 3x radical 2. And then this is over 2. And then those 2's are going to cancel out, and you'd end up with 5 plus 3x radical 2. And that is the answer. Right, so those 2's you could cancel. And I guess over here, those 3's you could cancel. All right. So I think that takes care of all the product stuff in this section. Now onto quotients, which basically work the same way. So if you have the same kind of root, so nth root of a, nth root of b, to keep things kind of general, and b is non-zero, because if b was 0, we'd be dividing by 0, and then we'd be in trouble. What you can do is you can write the quotient of the two roots as the root of the quotient. So it's another law of exponents, and that's, I mean, sometimes it works in that direction where you'd be going left to right the way that it's written there, but a lot of times it's right to left, and that's actually what's going on the rest of this page, because the square root of 24/49 is going to be easier to deal with if we rewrite that as the square root of 24 over the square root of 49. And then we just have to deal with them individually. That ends up being something that's effectively simpler, even though there are more roots. So the biggest Perfect square that divides 24 is 4. This already came up before, another problem. And then the square root of 49 is just 7, right? But then the square root of 4 is 2, so this is going to be 2 radical 6 over 7. All right, next one. Again, I think this is easier as the quotient of roots, so the cube root of 5p over the cube root of 27. Cube root of 27 is 3. In the numerator, we can't really do anything, right? The power of p is too small, right? It's 1. In order to simplify it, it would need to be at least 3. And then the 5, there's no perfect cube that's going to divide that, right? The smallest perfect cube that might help is 8, which is bigger than 5. So here that doesn't help. So the numerator is simplified as far as you could get it. It's the cube root of 5p. But the denominator, that's 3. The cube root of 27. Okay. Next, number 19. I think same idea. That's easier as a quotient of 2 roots. So we can rewrite that as the 4th root of 9y to the 5th over the 4th root of 16z to the 4th. All right, well then we can rewrite the y to the 5th and say this will be the 4th root of 9 times y to the 4th times y, right? Use the largest multiple of 4 that's less than 5, which is just 4 itself. And then in the denominator, 16 is a perfect 4th, and so is z to the 4th. So I'm going to break that up and write that as 2 4th roots. Let's see. So we can bring out the 4th root of y to the 4th on the top. And then the rest we won't really be able to do anything with. So we'll have the 4th root of 9y. But then on the bottom, the 4th root of 16 is 2. And then the 4th root of z to the 4th is z. So that takes care of the bottom. And then on top, I guess we could say, well, the 4th root of y to the 4th we could rewrite as a y. So we'd have y times the 4th root of 9y over 2z. And there's our answer. All right, so sometimes, like with 17, 18, and 19, it helps to rewrite the root of a quotient as a quotient of roots. Sometimes, like with 20, 21, and 22, it might help to go the other way. So with 20, we can rewrite that as a single root, and then we can simplify what's underneath the root first. And that may give us something that's easier to handle. So let's see, we've got the square root of 45 a to the 5th over 5a, and 45 over 5 is 9. And then a to the 5th on top, a on the bottom, that's where you can subtract exponents and say, well, then that's a to the 5 minus 1, or a to the 4th. But those are both perfect squares, right? We got the square root of 9 times the square root of a to the 4th. So that's going to be 3 for the square root of 9, and then the square root of a to the 4th is a squared. So that simplifies to 3a squared. You don't have to do this sort of thing the way that I just ran through it. You could actually do this one without combining it into a single radical. So what you could do if you were going to do that is, I guess then you would rewrite the numerator as the square root of 9 times 5, then times a to the 4th times a. So you'd want to use the largest power, or the largest multiple of 4 that's less than 5, which is 4 itself. And then we've still got the square root of 5a down here. So I'm going to break up the numerator into a product of roots, where let's see. Oh, did I say I need a multiple of 4? I don't need a multiple of 4 here in the numerator. Sorry about that. I need a multiple of 2. The largest multiple of 2 that's less than 5 is 4. I was thinking we were still on 19, I guess. That's got a 4th root. But what I'm going to do now is I'm just going to bring out the square root of 9 and then the square root of a to the 4th. And then we're going to have a square root of 5a left over. Then on the bottom, we've got a square root of 5a. All right, so then we're going to have 3a squared times the square root of 5a over the square root of 5a. And we've already said that the thing that's in the denominator should not be allowed to be 0, right? Because we can't divide by 0. So a can't be 0, right? Basically, that's what that comes down to. But that also means that the square root of 5a is non-zero, which means that we could cancel it. And you could say, well, then this is just going to end up being 3a squared. So you get the same answer. So you could do it that way too. Although, I mean, these problems are here to kind of have ones where it makes things a little simpler if you combine it into one giant root. That's not the only way that you can do it. But with 21 and 22, that's what we're going to do. We're going to make giant roots. So let's see then. With 21, that negative 2 is just going to stay out front. And then we'll have the cube root of 250n over 2n to the 4th. So negative 2 out front still times the cube root of 250 over 2 is 125. And then n would be raised to the power of 1 minus 4, which would be n to the negative 3rd. So I'm going to rewrite this expression underneath the radical so it has a positive exponent. So that would be negative 2 out front still times the cube root of 125 over n cubed. Right? Bring it down to the denominator, then you get a positive exponent. This might be easier to break this into a quotient of cube roots. So to write it as the cube root of 125 over the cube root of n cubed. So the cube root of 125 is 5. The cube root of n cubed is n. So you have negative 2 times 5 over n. But then you can multiply the 2 and the 5 and say this is the negation of 10 over n. I think that's probably the best way to write out the final answer. And look how simple it looks compared to what the problem was that we started with 21. Like that looks really, really simple, that final answer. And sometimes that does happen when you can combine things into one root. Sometimes you get a lot of nice simplification there. All right, so let's see what happens if we do the same thing in 22. So same idea, we're going to make this a big cube root. So cube root of 320 x to the 4th y squared over negative 5 x to the negative 2 y to the 5th. Okay, well then 320 over 5 is 64, so 320 over negative 5 must be negative 64. So then we can rewrite what's under the radical as negative 64 times x raised to the power of 4 minus negative 2, which is really 6, and then y raised to the power of 2 minus 5. All right, so that's the cube root of negative 64 x to the 6th y to the negative 3rd. And then I guess rewrite that with a positive exponent. So cube root of negative 64 x to the 6th over y cubed. And then we can break this up. We could write this, and I'm going to do two steps at once here. because we could break it up into a quotient of roots, but then there's a root of a product on the top, and we can break that into the product of roots. So I'm going to do that too, and say we're going to have the cube root of negative 64 times the cube root of x to the sixth over the cube root of y cubed. Then the cube root of negative 64, that's negative 4. Then the cube root of x to the sixth is x squared. And then in the denominator, the cube root of y cubed is y. And I think it would be more conventional to get that minus sign out front. But other than that, I think we got it. And look, it happened again. We got a relatively simple looking answer from an original problem that was pretty complicated looking. But again, sometimes if you can combine it into a single root, then that's the way that it works out. It tends to work out really nicely. I guess when you have problems that are designed for that specific sort of thing. All right, I think that would cover all the different things that would show up in section 6.3. The biggest thing, I think, is just kind of being familiar with the perfect powers, in a way. Because the toughest things to deal with the simplification tend to be the coefficients rather than the variables. So the perfect squares, I think those, like those tend to be pretty reflexive. You see them a lot, right? Maybe once you start getting into big ones, like bigger than like 144, sometimes they're hard to remember. Like maybe it's hard to remember that like 196 is what you get when you square 14. But then like the cube root, like I guess the perfect cubes and the perfect fourths, those are ones that you don't use as much. But then again, like once you start doing these, once you start doing the homework, the more they show up, the more you remember them, right? The more times that you see that you have to use a 16 as a perfect fourth, the more you're going to remember that that's a perfect fourth. So the homework kind of reinforces that, and that's a good thing because it's not like these roots are going away, right? They're going to keep showing up throughout chapter 6. But that, I think, is the biggest thing in this section, is just simplifying the coefficients if they're ones that use unusual perfect powers, or if they're ones where you wouldn't be able to see the perfect power right away necessarily.